Hello everyone, I'm Yuwei, a second-year PhD student from Imperial College, and today I would like to share my recent work about a computational node model for proton exchange membrane fuel cells. So generally, a PEM fuel cell usually have 7 layers, and among these layers, the gas diffusion layers, catalyst layers, and the membrane are together called the membrane electrode assembly, and is always considered at the heart of the PEM fuel cell. So as the operation of PEM fuel cell involves processes happening at different length and time scale, so the current modeling works are often focusing on 3 categories: the empirical model, continuum model, and data-driven model. Among these model types, the empirical model is considered as the least accurate one, but due to its lowest computing cost, it is still favored by several applications, including lifetime assessment, real-time status estimation, and large-scale simulation. The classic empirical model is derived from 4 basic equations. So although it is based on a lot of simplifications and assumptions, it includes all 3 major sources of potential drops of PEM fuel cells, and it can fit well with the experimentally acquired polarization curves under given temperature, pressure, and humidity. So, however, this model does not include any internal status of the cell, like the water content in membrane and the local liquid water saturation. So this model is only its accuracy is limited to a very narrow range of working condition once the model parameters are set. So many efforts have then been paid to enhance this simple model to overcome this limitation, like introducing overpotential gradient, two-phase flow, and membrane water transport. So with these modifications, actually the empirical model have included all the major transport and reaction processes, and the descriptions of these mechanisms are essentially the same as the 1D continuum model. However, all these studies are based on a common homogenized assumption of uniformly distributed scalars, transport properties, and source terms. So although they can use the same set of parameters as the 1D model, they cannot reach a comparable accuracy. So to solve this problem, this study starts from a different perspective, the direct reduction of a 1D model. And the major contributions are an order reduction method, the determination of transport properties, a simplified 1D catalyst layer electrochemical model, and the analytical approximation of average membrane hydration status. So to describe the operation of PEM fuel cell, this study adapted the partial differential equations of an open source one-dimensional steady-state model that is available in the literature. So most of these partial differential equations share the same general format except the ionomer water transport, which has an extra term accounting for the electro-osmotic drag. So in this study, the 8 partial differential equations are reduced to 6 computational nodes that are located at the boundary of each cell component. And taking one cell component as an example, the fluxes between the computing nodes can be described by the conservation equation. And by using a lumped transport coefficient and linearly distributed source terms, it can be further reduced to a linear equation that only includes the status of the neighboring computing nodes. However, there are 2 exceptions, and the first one is that this linearly distributed source term is not applicable for electrochemical reactions. And the second one is related to the ionomer water transport, which has an extra term. And this extra term standing for the electro-osmotic drag will be approximated with an analytical approach. As described previously, this model uses lumped transport properties, but these transport properties are still dependent on the local status of the cell. For transport properties with mild gradient, it can be simply calculated by its value on the two neighboring nodes. But for those with large gradient, they are computed based on a linearized distribution of the scalars to avoid a large error. The electrochemical reactions in this work are described by the BV equation. Depending on the parameter of the reactions, the same equation has a very different behavior on the anode and cathode side of the cell. On the anode side, the hydrogen oxidation reaction has a relatively fast reaction kinetics, but the anode ionomer has a very large resistance for proton conductivity. So its current flux in the anode ionomer is highly unbalanced, while on the cathode side, the oxygen reduction reaction has very sluggish reaction kinetics, while the proton conductivity is relatively high, so the current flux is relatively linearly distributed. So two different modeling approaches are applied for different side of the cell. For cathode side, a simple lumped model is used and an analytical solution of the BV equation can be obtained. Then the electroosmotic drag is approximated similarly to the source terms. But for the anode side, a simplified 1D model is developed, and the electroosmotic drag is estimated using the same approach as the transport properties. However, the electroosmotic drag in membrane, however, is estimated by an analytical approach. So since there are no source terms for the water transporting membrane, so the total water flux and proton flux remains constant. Accompanied by the lumped transport property, the conservation equation, the analytical solution of the conservation equation can be obtained. For both the average membrane water content and the electroosmotic drag. All these partial differential equations are then organized into 4 submodels, and these submodels are connected with the segregated approach. 2 of these submodels are solved numerically using self-written solvers. Then the modeling results are validated against a 1D model. So the simulated polarization curves agrees well with the 1D model, but the computational node model tend to predict a lowered limiting current, and this can be explained by the internal status of the cell. These internal status are also validated, but under the same working condition as 3 different current densities. So as you can see in the figure, the current flux, the highly unbalanced current flux in anode catalyst layer is successfully predicted, and the liquid water saturation at these computing nodes are also captured, but the nonlinear distribution of it is ignored. This figure shows the ionomer water content. Although it seems that the error is higher on the cathode side, actually the smaller error at the anode and membrane boundary has a larger impact on the overall simulation results. This table shows the detailed values of the membrane resistance computed by the 2 different models, and at both high and low current density, the computational node model predict a similar membrane resistance at the 1D model, but at the limiting current, the membrane resistance of the computational node model is 75% higher comparing to the 1D model, which is a major reason of this underestimated limiting current, and it is due to this faster dehydration of the ionomer. And this higher membrane resistance can also lead to a higher heat generation rate, and this larger temperature gradient can further accelerate the membrane dehydration. So this is a positive loop, and it can further worsen the problem. With these self-written solvers, the computational node model obtained the similar simulation result as the 1D model, but it is nearly 100 times faster comparing to the original 1D model. So in summary, in this work, a computational node model is established based on the reduction of a steady-state 1D model of PEMFCs cells. The model is 2 magnitudes faster comparing to the 1D model, while predicting similar polarization curves and internal status. The limiting current is underestimated due to the faster membrane dehydration and the higher temperature gradient. So it should be noted that since this model is a reduction of the 1D model, it also shares the same limitations. And the major one is that it's negligence of the gas channel. And so this model is only applicable for cell with a very small active area. So one future work is to integrate this model into a hierarchical modeling framework. So the gas transport in the gas channels can also be included. So that's how. Thank you very much for listening.